In this video, we are going to discuss one use of beta distribution in Bayesian machine learning. Now, this is a somewhat heavyweight topic, so let's start with something which is easier and has nothing to do with the beta distribution. Suppose that we have a box with 3 red and 2 green balls, from which I draw a simple random sample without replacement of size 3. In other words, I put my hand in the box, mix them up and pick any 3 balls. They may be red or green, so I just denote them X, X, X. Now that is the first stage of our experiment. In the second stage, I draw an SRSWR simple random sample with replacement of size 5. By this I mean I pick any one of the balls, notice its color and then put it back. Then again draw another after mixing. I notice the color and in this way I do it 5 times. Suppose I get R all the time. So all the time I get only red balls. I have not told you what you got after the first stage. I am telling you what you got after the second stage. Now my question is, what is the chance that all these balls were actually red? So symbolically I can say I am interested in this conditional probability that in the second stage I have got all R's. Given that, what is the probability that after the first step all these X's were actually R's? Now we already know how to attack this problem. We draw a tree-like diagram where we list all the possibilities that can be for these 3 X's. It could be all green, 1 red, 2 green, 2 red, 1 green, or all of them are red. Now you might be wondering why I am not writing G or G. The ordering here is not important. I am just writing down the composition. So 1 red and 2 green. Whether the red comes first or the red comes next, I am not distinguishing between them. And then from this, any of these things may result. And similarly, this may result from these things. Then we work out all the probabilities. I am not going into the exact computation, just the overview. We compute this. Suppose I call this P0. Similarly, P1, P2, P3. So the probability that you get 1 red and 2 greens in the first step, I call that P1. Now, if you are here, there is a probability that you will get this. So these are also probabilities that I will denote by Q0, Q1, Q2 and Q3. By the way, you can easily understand Q0 will be equal to 0. If all these balls are green, how come you are getting red balls out of them? Now, this was computed in this pictorial intuitive way. You are interested in this particular thing. So find out the probability of this path, that was P3 Q3, and you divide that by probability that you at all come to this. Now you can come to this following any of these 4 paths. Of course, this path is really not existent, but if I just write them down, all of them, it will be P0 Q0 plus P3 Q3. So the total, out of that, I am interested in only one single path. That is basically an application of Bayes' theorem. So far there is no machine learning and there is no beta distribution. Now we are going to get into that. So this setup that we saw just now can be thought of in a somewhat strange manner. Think of it as if, in this case, we are actually performing a coin toss. We are tossing 5 times and think of red as head and tail as green. So in this case, I say I am tossing a coin 5 times, I get head all the time. Now what is the coin that I am tossing? Let's take this one. If it is RGG, if in your box you have got 1 red and 2 green balls, and you pick one of them at random, what is the chance that you will get a red? It is 1/3. So it is like a coin with probability of head equal to 1/3. Similarly, this is a coin with probability of head 2/3. This is a Cholet coin, probability of head equal to 1. Similarly, this is also a coin which has both the faces are showing tail. So as if I am picking one coin at random. So I have 4 different types of coins and I am picking one at random, not equally likely with certain probabilities. Then I am tossing it 5 times, and based on that I am trying to find out what is the chance that the coin that I picked had head on both sides, because this corresponds to a coin which will only produce head because there is no G here. So given that 5 consecutive tosses all showed head, what is the probability that the coin that you have in your hand actually has heads printed on both sides? Now in this toy version, the probability of head can be either 0, 1/3, 2/3 or 1, nothing more. Now we are going to make a more complicated version where the probability of head can be anything between 0 and 1. So this is no more a finite set but a continuum. So the probability can go from 0 all the way up to 1. So this is your starting point. So you can have one arrow going to this, 0 probability, another arrow going to this, 1 probability, another arrow coming half. So there are uncountably infinitely many arrows. It's like a spray of arrows. Now whatever is the value here, suppose I take one value which I call P, then there is a chance that that particular coin, when tossed 5 times, are producing only heads. So for each one of them you have a similar arrow. Again there is a continuum, a spray of arrows like this. So it is very much like the last diagram, except that now we are working in a continuous setup. So we need some way of giving weights to these things. Earlier we had P0, P1, etc. So we need to give them some weights. Because it is a continuum, it is only natural that you will give them weights using some density. Now let's take a very simple example where I have no clue as to what is the probability of head of my coin. Absolutely no clue, which means each one of them is just equally likely for me, so I give all of them weight equal to 1. In other words, I am trying to make this statement that the random coin that I have picked, that has a probability of head. Because the coin is picked randomly, so its probability of head is also a random quantity, and I want to denote it by some capital letters, so I have used the capital pi for that. Capital P being already reserved for probability, so I am using capital pi. I am basically assuming that this follows uniform 0-1 distribution. I have no clue as to the bias of the coin that I have picked up. Anything from 0 to 1 is just equally likely. Now, suppose the coin that I picked actually has probability of head P, then what is the chance that it will produce all heads in 5 consecutive tosses? That probability is P to the power 5. Now my question is, given this additional information that the coin has produced 5 consecutive heads, what is the chance now? What is the likelihood of the probability being actually P? So I am interested in finding out the conditional density of capital pi given that I have seen this. And I will use exactly the same analogy, whatever we did earlier. I will find out this particular path that passes through this. It is 1 times P to the power 5. And downstairs I will divide by the total of all possible paths. In this case, because there's a continuum of paths, it will be just the integral. So upstairs you have P to the power 5. Downstairs I will have the integral 0 to 1 P to the power 5, which is simply 6 times P to the power 5. P lies between 0 to 1. And we quickly notice that this is also a density over 0 to 1. Now think of this as beta 1, 1, and in that case this is actually beta 6, 1. So if you started with this belief that everything is equally likely, then after seeing this particular outcome, 5 consecutive heads, your belief is reshaped into beta 6, 1. So pictorially, this was your original belief. It was just flat at 1. Now after you have carried out this experiment, your belief after looking at this data is the beta 6, 1 density, which is essentially the graph of p to the power 5. And you see this graph is increasing near 1. So your belief says that most likely it is the probability of head is close to 1. That is why I am getting so many heads. So you see how your belief changed as the result of this Bayesian computation. Now this is what actually happens in Bayesian machine learning. You start with some level of belief, or this is your state of knowledge. You are not exactly sure what is happening, but you have some state of knowledge. Then you collect some data, that is some cases are fed into your system. You learn. And when you learn, you update your belief or your state of knowledge, and this is the updated version. So people call this thing the prior, and this one is called the posterior. Now it is not very difficult to see that even if I change this to some other beta, not necessarily 1, 1, in that case, this will also be some other beta A prime B prime. So whenever you use beta to start with, after the entire process, whatever is your data, you will always end up with another beta. And this helps in computation of the updated information easily, because you collect some data or some data streams in and you update to this beta. Now when some further data streams in, you consider this as your input, and again you compute the updated thing. Because you are always inside the beta family, the same formula may be used again and again. Well, that is the main idea. There is a lot of other details that I am glossing over here. The video is already too long, so let me stop it right here. Well, in this exercise, you are required to just do the same computation all over again, but this time you start not with uniform 0, 1, but pi has beta 6, 1 as its prior distribution. Now I give you the extra information that when I toss the coin 5 times, I get 2 heads and 3 tails like this. What will be the posterior now? So you work out what the probability here is, and these are no more ones. These are given by these values, and you should come up with the corresponding 2 quantities, 2 parameters for the posterior beta distribution.